For this problem, we're trying to figure out the equilibrium constant for this reaction under certain conditions. So we have a balanced equation, that's important, and we know that we start with 0.01 molar hydrogen, 0.008 molar iodine, and after this reaction mixture comes to equilibrium, the iodine concentration goes down to 0.0056 molar. So we have to figure out what are the concentrations of all three of these species at equilibrium. We know that the hydrogen concentration is also going to go down some amount, and the HI concentration is going to go up from 0 where it starts. And because there's a stoichiometric coefficient of 2 in front of the HI, we know that its concentration is going to go up twice as much as the H2 concentration goes down. So it gets pretty complicated, as you can see. And the best way to keep this straight is to do an ice table. You don't absolutely have to do an ice table, but I need to do one because I'm not smart enough to keep track of all this without organizing my numbers. The first letter of ice, I. This means initial concentration. The C in ice stands for change, and the E stands for equilibrium. And those three are going to be the rows of our table. The columns are going to be the three species involved in our reaction. We have our reactants H2 and I2 and our product HI. And what we really want to figure out is the E row, because once we know our equilibrium concentrations, we can calculate Kc. And it's given that the equilibrium concentration of I2 is 0.0056, so we can go ahead and put that in there. And it's given that the initial concentration of hydrogen is 0.01, and the initial concentration of iodine is 0.008. And we're assuming we start with 0 HI. Now let's look at the change. So specifically the change of iodine, because we know what it starts with, 0.008, we know that it ends at 0.0056. So we know that the difference is, 0.008 minus 0.0056, and that would actually be a negative value because we're losing iodine. But even though we could put a number there, let's just put x, because we can compare the change of the hydrogen and the HI to the change of the I2. So because there are stoichiometric coefficients of 1 for both the H2 and the I2, that means that if we lose X amount of concentration of I2, we're also going to lose X amount of concentration of H2. But then there's a 2 coefficient in front of the HI, so that means that if we lose X, I2, and H2, we're going to gain twice as much HI. I'll put a plus there to show we're gaining it. Now for the equilibrium column, we know that if we start with 0.01 H2 and we lose X of it, we're going to just end up with 0.01 minus X. And if we start with 0 HI and we gain 2X of it, we end up with that. Now we can go about solving for X. Just looking at iodine, we can set up this equation, and solving for that, we find that X equals 0.0024. So we can replace X with that actual number in these equations for equilibrium concentration, like that. And doing the simple math, we find that our equilibrium concentration for hydrogen is 0.0076, and for the HI it's 0.0048. So now we just have to come up with our equilibrium constant expression, which is concentration of products over concentration of reactants, like that, and then put in the numbers we just found for the equilibrium concentration values. And if you run that on your calculator, you should get 0.541 for the equilibrium constant.
Made with Doodlecast Pro.